Hi, I'm Ben Hansen, and in this short video I'll explain what viscosity means. There are lots of different kinds of liquids and some flow more easily than others. You might have heard the word viscosity used to describe thickness, but is that correct? And what about two liquids which look quite different like this? Which one would have a higher viscosity? Let's find out. Liquids flow when a stress is applied, which could just be their own weight due to gravity. We can describe liquids by the way they flow under stress. But first, we've got to be specific about what we mean by flow and how to measure it. So let's start by looking at some of the ways materials can change shape. I can demonstrate with this block of Play-Doh here. This is compression. This is extension. And this is torsion. All these movements can happen within liquids too, but mostly we're considering liquids flowing over a surface. So let's take a look inside that motion. Liquid usually sticks to surfaces, so right at the very edge there's a thin film of liquid which is barely moving. Then as you move further away from the wall, the flow gets faster. If we imagine a small section of the liquid within, the main way it's deforming is called shear. That's measured as the distance along the direction of flow divided by the distance across the direction of flow. The rate at which it's deforming is called shear rate. Shear rate is not the same as velocity. We can see if we look across a channel, this could be a pipe, then the fluid's velocity is fastest right at the centre. But in terms of shear rate, well, the shear rate at the centre is actually zero because the neighbouring elements of the fluid are flowing together. They're not moving relative to each other. The shear rate is highest at the walls. So now we've seen that shear rate describes flow at specific points within the fluid, but how does viscosity affect flow? Here we have a simple made-up situation where three different liquids all flow down the same slope. The shear stress on each is the same, but they flow at different rates. And that's because they have different viscosity. There are lots of adjectives we could use to describe the liquids, but viscosity gives us a numerical scale to define them. Time for the first graph. The usual way to draw this is to have shear stress on the vertical axis. In this case, all three liquids had the same shear stress. The horizontal axis is the shear rate, and the three liquids flowed at different rates. C flowed the slowest, and A was the fastest. The viscosity of each liquid is defined as the shear stress divided by the shear rate. The viscosity of C is highest, and the viscosity of A is lowest. So to measure viscosity, you need to measure shear stress and shear rate, and that's the way it's done in a lab using a rheometer. One way to do that is to trap a thin layer of liquid between metal surfaces, rotate one surface, and measure the torque and speed of rotation. It's maybe worth noting that you're never actually measuring shear stress or shear rate directly within the liquid, but extrapolating them from the motion and stress on the metal surfaces, which you can measure. One way to think of viscosity is the amount of stress you need to apply to make a liquid flow at a certain rate. The more stress you apply, the faster the liquid will flow. Simple liquids like water have a proportional relationship, so if you double the stress, you'll double the flow rate. That's Newtonian viscosity. The slope of the shear stress versus shear rate graph is the viscosity of any liquid. Some oils and syrups are also Newtonian. But very often liquids don't have that ideal straight line relationship. Most thick fluids you encounter in real life are non-Newtonian. Fruit juices, smoothies, sauces, soups, salad dressings, toothpaste, paints, and cosmetics are all non-Newtonian. In all those cases, it's not a disadvantage, not at all. It makes the paint easier to control, it makes the dressing stick to the salad, and it means it's not a great deal of effort to drink a smoothie. But it does mean that we can't describe any of these liquids with one measurement of viscosity. Those products I mentioned usually have this form of curved relationship. This is called shear thinning, and I'll show you what that means. At a low shear stress level, they would flow very slowly, sometimes barely at all. And that means that their apparent viscosity is very high, If a material's not flowing fast, then it looks like a very high viscosity material. But as you apply a little more stress, the rate increases disproportionately more than it would for a Newtonian liquid. Under those conditions, it would apparently feel like it had a lower viscosity. It doesn't mean the liquid's changed into a different material. The apparent viscosity is just reflecting that moment in time under that flow condition. So one material can have a range of different apparent viscosities depending on how much stress is applied. Non-drip paint is a classic example. It's almost solid in the pot, but using a brush you can apply a thin layer to a wall very quickly without too much resistance. And then when you take your brush away, the paint stays on the wall, it doesn't immediately dribble down. Foods can be similar, like this pudding. It's thick enough to stay on a spoon without pouring off the sides, but when you put it in your mouth, your tongue can compress it and you can swallow it effortlessly. This also shows that you can't tell how thick a product is just by looking, because this looks like a solid. So in this video, we've seen how viscosity is defined and how it can be used to describe Newtonian liquids like water and some oils or honey. Most other liquids are non-Newtonian and their apparent viscosity depends on the stress being applied. Often that makes them much more useful and interesting, but in this case it does mean that you can't simply say one of these liquids has a higher viscosity than the other. In part 2, I'll show some of the ways you can measure and describe non-Newtonian liquids. Thanks for watching.